So this is chapter 3. It's really just section 3 of chapter 3. But we're going to start to talk about the atom in some more detail. So let's get the basics established. 3 subatomic particles make up the atom. And you've probably known this since, I don't know, 3rd grade, 5th grade, 7th grade. I don't know when the first place that you get this is, but 3 basic subatomic particles: protons, neutrons, and electrons. Protons and neutrons are in the nucleus. They're down in the middle. And electrons are zinging around outside. That's the first thing you got to know. If we start off talking about the nucleus, we're talking about 2 specific subatomic particles, protons and neutrons. Protons are positive. I am pro-nucleus. You're positive about the nucleus. You probably can all remember that, but and I think you probably all get that pretty well hammered into your heads in physical science. Protons have a positive charge. Neutrons have no charge. But let's talk a little bit about mass. Let's talk about mass, shall we? It's time to talk about mass. So, what do you notice about the mass of a proton and the mass of a neutron? They're very, very, very close. I mean, this is times 10 to the negative 27th. So we're talking about, a whole lot of zeros. And the same exact thing, and that's not to scale, obviously. They're pretty darn close. They're almost identical. Are they identical? No, they're not. There's a slight difference in the mass of a proton and a neutron. But they're so, so close. That becomes an important point in just a little bit. What happens when you put 2 things with the same charge together?
They repel each other.
Traditionally, yeah, we think of them as repelling one another. So we've got this nucleus that's densely packed with protons that have a positive charge and neutrons that have no charge. How on earth does it hold together? So normally those protons would repel one another because we have proton-proton repulsion. In the case of the nucleus, there's this weird thing called nuclear force. It's one of the, 4 fundamental forces of the universe. And it actually helps hold the nucleus together. The neutrons in there also help stabilize the nucleus. And there does come a point, we can get the bigger the nucleus gets, the harder it is for those nuclear forces to overcome all that repulsion. But up to a certain point, those nuclear forces can hold a nucleus together, and it's very, very stable. It doesn't break apart. When we get up into really, really large nuclei, those tend to be elements that are radioactive. They give off nuclear radiation. They actually have chunks of their nucleus flying out into space. That's nuclear radiation. That's what it is. It's an atom whose nucleus is decomposing. It's breaking down and throwing off pieces or energy. And that's the point at which nuclear forces can no longer overcome all that repulsion. So that's an important thing to know. The radius of a nucleus, I don't care if you ever memorize that number. What I want you to know is that an atomic nuclei is really, really small, which you already knew. But we're measuring this in picometers, and it's not even a whole picometer across. It's 10 to the negative 3rd picometers. That's insanely small. That's minuscule. That's beyond the scope of our imagining. This is where you find out exactly how creative the sorts of people who go into the fundamental sciences are. We measure the atomic mass of atoms. They have a mass, we can measure it. We measure atomic mass in, are you ready for the units? Atomic mass units, because they're the units that we use to measure atomic mass. Isn't that creative and clever? Not particularly. And then that's abbreviated AMUs, and you've used these before. Notice that we don't measure these things in grams, picograms, micrograms, milligrams, kilograms. They're measured in their own whole separate thing, atomic mass units. And remember what we said about the mass of a proton and the mass of a neutron? I mean, that's pretty darn small, and that's, I believe, in grams. I'd have to go back and double check. We take those and we say, okay, you know what, they're close enough. 1 AMU is just one of those. We kind of take an average, shoot the middle, and say, one proton has a mass of 1 AMU. One neutron has a mass of 1 AMU. We call it even. They're so close that we fudge the numbers on this gigantic scale. It seems daring and mad and dicey and risky, but it's what we do. So, you know, the AMU, and you're never ever going to have to define this or know this, but, you know, an AMU corresponds to some mass in grams. Don't get hung up on it. Just kind of forget that. One proton has a mass of 1 AMU, one neutron has a mass of 1 AMU. And electrons have such a tiny little mass that we don't even talk about them. They're really that light. Now that we know how we measure the mass of an atom, we can talk about isotopes, because we have to know about mass to talk about isotopes. Because an isotope is just, well, actually, no, we'll do this first. An isotope is an atom of some element that's got a different mass. Okay? So we'll take carbon as an example. We have carbon 12, C12. It has a mass of 12. We have carbon 14 that has a mass of 14, once again with the inherent creativity and cleverness of chemists and particle physicists. Isotopes are named for their mass. The mass of uranium-238 is 238. Woohoo! If you have an isotope of cobalt with a mass of 60, guess what we call it? Cobalt-60! Yeah. So, I'm not above putting a question like that on your test, and you'd be amazed that a few people miss them every year. Like, what is the mass of carbon-14? 14 AMUs. Yep. So, isotopes are named for their mass. We can figure out how many neutrons are in any given isotope. So let's take carbon-12. Okay, carbon has got 6 protons. 1, 2, 3, 4, 5, 6. In its happy little nucleus. Each of those has a mass of what? 1 AMU. So the protons alone have a mass of 6 AMUs. If we're talking about carbon-12, how many neutrons do they have? 6! Woo! Because we just take the mass minus the atomic number, because the atomic number is equal to the number of protons. You remember that from physical science? Okay. So atomic number is equal to the number of protons, and you find that typically on the periodic table. And what you get when you subtract those is the number of neutrons. Okay? Okay, so working from the practice sheet, we looked up boron. We found that it's got an atomic number of 5, which means it has 5 protons. And we're given the number of neutrons it's got. So what's the mass of boron-5? Or I'm sorry, of this isotope, of boron? 11. This is boron-11. What about that electrons column? So this is where, when we said that we want to make sure that we don't confuse isotopes and ions, right now we are talking about neutral atoms. So a neutral atom has an equal number of positive and negative charges. So whatever your number of protons is, if this is a neutral atom, guess what your number of electrons is? Same thing. It's identical. Okay? So you can, from the information that you're given, you only need 2 pieces of information on each column. you can fill out all of the rest of this. And this is just kind of a practice thing. What I'll do right now is I'll give you time to do, let's say, 3 on your own. Remember that the key is on the back. You have the ruby slippers, Dorothy. So I'll give you time to do 3 on your own and make sure you're... Okay, when we write the name of an isotope, we have 3 ways to write it. And I guess I should back this up. The most basic is to write out the full name of the isotope plus its mass. So that's called hyphen notation. Carbon 14, cobalt 60. So for an isotope of lead with an atomic mass of 207, how would you write that? Lead 207. Okay. And hyphen notation is typically shortened up a little bit, and we don't write out the full word. So carbon 14 becomes C14. Cobalt 60 becomes CO 60. And lead, my favorite atomic symbol, no lead in your peanut butter sandwich, becomes PB 207. So that's pretty easy. So if I ask you about an isotope of phosphorus with a mass of 32 AMUs, Gesundheit, write me the hyphen notation, short and long form. So an element of phosphorus with a mass of 32 AMUs. Okay, the other one is symbol notation, and symbol notation looks like... So for our P32, what we would show for symbol notation would be a 32 up here, and we would have the atomic number down here. So that symbol notation gives us both the mass and the atomic number. So practice this by writing, well, let's do one together. So for cobalt... Okay, for cobalt 60, write the symbol notation. So we start off with the atomic symbol, CO. We have the mass up here, and we have the atomic number down here. Pretty easy. Let's do my old favorite, uranium-238. Go. That's all that is, symbol notation. It's pretty straightforward, pretty easy. This one's less commonly used. This would be more likely to be used in the context of like a really technical chemistry journal of some sort. Most of the rest of the world, when they're talking about isotopes in medicine, in engineering, and anything like that, they're just going to use hyphen notation because nobody but chemists cares about how many protons anything has. Okay, so one among your numbers said, but wait a minute. I thought phosphorus had a mass of 31. That's fantastic. I should have paid you $0.25 to say that. Sorry. Should negotiate for better recompense. You have learned all this time about the periodic table that the mass is... So, okay, let's look at phosphorus. What does the mass on the periodic table say for phosphorus? Okay. 30.97. Now wait a stinking second. 30.97? That's not a whole number. Where do we get our mass? From the atomic number, the number of protons, plus the number of neutrons. Well, each of those is 1 AMU, is it not? So how do you get 0.97 AMUs? I call baloney. This has got to be wrong. Something's terribly, terribly amiss. How do you get a part of an AMU? No, we completely disregard. The poor electron is like you know, I don't know, the puppy in the litter that nobody loves. I mean, nobody cares about how much electrons weigh, what their mass is. Nobody cares. So how do we get 0.97? No, see, no, you good. I know, good idea, but no.
It's from the numbers that you get in
No. What was that, Hannah? Oh,
average isotope.
it's an average mass. If we were able to take every single atom of phosphorus in the entire universe, it's a lot of phosphorus. If we took every single atom of phosphorus in the entire universe and we had a little tiny scale, and we set you to work now and you worked through your lifetime and through probably your quadruple great-grandchildren's lifetimes, massing every single atom of phosphorus in the entire universe and carefully recording your data, and you averaged all of those numbers, you'd get that. It's an average. There is not an isotope of phosphorus anywhere. There's not an atom of phosphorus anywhere that has a mass of 30.97. Okay? 31, yeah. 32, sure. 30, yeah. Maybe a weirdo with 29. But there's not an atom of phosphorus that has a mass of 30.97. The mass of the individual isotopes are given in whole numbers, and we average them and we get this number. So, often, if you round that average, the closest whole number to that average is your most common isotope. So if you had to take a flying guess, what do you think is probably the most common isotope of phosphorus?
31.
Probably 31 AMUs. Now, that's not always the case, because we could have something that has an average mass of 20.740 and doesn't have an isotope of 21. It's got an isotope of 19, 20, 22. Okay? That can happen. And I don't expect you to predict that. Know that very often or usually, rounding that average mass gets you the most common isotope, but not always. So it's not foolproof. How do you do a weighted average? Tremendous variation we have in this county and in the neighboring county. If you drive over the line into Beaver County, the price of gas goes up about 15 cents. Have you noticed that? So never fill up in PA, always fill up in Ohio. So let's say we got 3 gas stations and we want to figure out the average price of gas in an area. And I got $3.29 a gallon, I got $3.34 a gallon, and I got $3.49 a gallon. What's the average price of gas in this area? So we've got an average price of $3.37 and 33333 per gallon, because this is gas prices we're talking about here. Okay, and you all know how to do an average. How did you do that average? Add them all up and divide by the number you got. Okay, good, smart critters that you are. Now let's change the scenario a bit. Okay, let's say that I went to a few more gas stations and I found 3 gas stations that are selling gas for $3.29, 2 at $3.34, and 1 at $3.49. Figure out your average now. Okay, so we have an average now of $3.34 per gallon. There are a couple different ways you could have done this. There's more than one way to skin this cat. So you could have punched in 329 plus 329 plus 329 plus 334 plus 334 plus 349 divided by 6. You could have also done 329 times 3, close parentheses, plus, parentheses, 334 times 2, plus 349, divide the whole mess by 6. Gets you the same answer, right? Okay, let's change the scenario yet again. Okay, I've added a few gas stations. I've now got 4 with 329, 2 with 334, 4 with 349. Okay, what do we have for our number? Justin. Okay, we're getting an average of 338 per gallon. Okay. Now you notice that we had 10 gas stations here. Did anybody do the whole multiply this by 4, multiply this by 2, multiply that by 4, divide by 10? Okay, good. Let's set that up another way. So this is what you did, right? What's 4 divided by 10?
40%.
It's 0.4. What's 2 divided by 10? It's 0.2. It's also how you express a percentage as a decimal. So, is it fair to say, is it true to say, that 40% of the gas stations we looked at had a price of $3.29? 20% of the gas stations we looked at had a price of $3.34. And 40% of the gas stations we looked at had a price of $3.49. Interesting. This is a weighted average. So what we did in effect, if we had 100 gas stations that we had looked at, and we found 40 of them with this price and 20 with this price and 40 with that price, it wouldn't change the fact that really what we're doing here is multiplying by 0.4, and here what we're doing is multiplying by 0.2, and here we're using our 0.4 again. So the alternative way to set this up, which is much simpler and much cleaner and much prettier, we can do this. That's a weighted average. We take whatever value it is that some proportion of our sample has, and we multiply it by the percentage of the sample that has that value. That's all a weighted average is. It's very, very simple, but for some reason it confounds people in the weighted averages on atomic masses. So now let's actually walk through an atomic mass example together, okay? So, what is the average atomic mass for an element which exists with the following isotopes? Mass and abundance. 60 AMUs, 58 AMUs, 61 AMUs, 0.75%. Okay, how do we find this? Well, it's really easy. We take the percentage times the mass at that percentage and add them up. Now, you have to convert that percentage to a decimal form. So this is going to look like, okay, and with a few corrections to my own decimals, we go ahead and work this out. Okay, so we set this up with the percentage that we have for each isotope and the mass of each isotope. And what we get is an average atomic mass of 59.8125 AMUs. Now, we can only have, I think you were given one behind the, you were only given 3 sig figs. Well, we'll assume that had one more. So if you have 3 sig figs, then your average atomic mass is 59.8 AMUs for this isotope. Okay, so that wraps it up for weighted averages. We'll pick it up tomorrow.